So now let's go and look at some really cool things. So this was our robot before our season ended. So right at states, unfortunately we didn't make it to worlds, but it is what it is. But this was one version of our robot. If you see our actual robot now, we kind of switched up the position of these servos. But right now I'm going to demonstrate to you the power of joints. Okay, joints are some of the most powerful things in Fusion 360. In Onshape, they pretty much have joints on by default. Then again, Onshape was created by SolidWorks, and SolidWorks has something called mates. Mates are essentially joints. So we use a couple of joints here. We use two rotation joints on the servos, and rotation joints on the fixed positions on the chassis to create this kind of motion, to demonstrate this motion. Now we also use slides. We use slide joints to demonstrate the slides motion, as well as over here we use slide joints. But as you can see, actually, as the slides go up and down, they're paired with the motion of the motor. The motor has a revolute joint, and this joint is motion linked with all of these joints. So I'll actually go into detail on how all this works after I demonstrate how joints work and the building systems and things like that. First off, the most important thing in FTC CAD is knowing how things go together, right? So you need to have a base instinct on, okay, well, here's how Rev works, here's how GoBuilder works, here's how GoBuilder type things work, here's how Rev type things work, right? So, for example, one big failure of a lot of early CADers is that they know enough about CAD. That's fine. They just don't know how things really work in the real world. Because CAD can very much skew your perceptions of how the robot should be built, how the robot should be working according to how it's built. So, for example, on this robot right here, our linkage system, the way it was right here, didn't work at all. Because in CAD, the perception was that it did based off the motion links. But in real life, like that kind of physics doesn't apply. If you want your thing to be straight up and down, you have to apply basically infinite torque to make this go, which would never work, of course. So that is really important to know for any CADers out there. Like you need to know that your CAD model may not reflect reality. That's why I generally recommend that people who know how to build, so builders, just hobbyists, learn how to CAD after they understand how the systems work. But for right now, I'll just go through quickly how things work in Rev or GoBuilder, depending on what you're using. So we're going to look at some Rev parts first. Now, what I'm pulling in is a component, right? So let's go through the hierarchy right now. What you just saw is this is the parent component, and I just inserted the child component. So one of the child components. What that means is I basically dragged and dropped, or right click and press insert into current design, another component that was already made, which are all this stuff is on Rev's website or GoBuilder's website. If you search for a part, like actually I'll just do that right now. I'll show you. So here's my alt, right? And I'm just gonna go to GoBuilder, right? And let's just say I want like a 2-hole pattern plate. Here's a two-hole pattern plate. Now I can go here and download the step file. Okay. From here you can take your step file and press upload and drag it and drop it here. And it'll upload it into the folder that you want. From there you can save the design you want to work in and drag it and drop it from your side menu. Right? Now that we have this, I'm going to show you how things work, right? So you have your parent component, which is every single component that you have in your design. So now I've inserted another component. Well, now this component is just here, right? But it's now part of the parent component. Now, the parent component is both these components together, all right? Well, now I want to put these components together. How am I going to do that? You can press M to move or rotate a component by selecting it in the browser. And then you can change the angle at which you want to rotate it. From here, you can select a circle with the joint tool, which J is your joint tool. So when you press J in your shortcuts, you're going to get your joint tool. Now, I'm basically selecting the joint right here. And then for Rev, I can just go into the channel and select this point here. Now you see it kind of went through the model. You don't necessarily want that. So joints give you a very nice feature of being like, okay, well now you can move back a little bit and really align yourself. Now we're lined up. And I can easily turn this into a slider joint along the x-axis. There we go. So now we're sliding along the x-axis, right? So what you just saw was how Rev goes together. What you need to kind of understand is that Rev works with a series of these channels. Okay, so the screw heads of the Rev screw heads fit into those channels, and you can put different plates onto those screw heads and tighten them with nylocks. So I'm actually going to show you something pretty cool here. As part of IB, which is the school I go to, you have to do this thing called an IA for every single one of your classes. It's essentially a small research paper about a research question that you're trying to find out. For example, my physics research question was to what extent does the angles of a joint in a two axis arm affect the force on that arm? And of course, I use torque equations and things like that to find that force to to use servo ratings and things like that. But in order to do this, I had to borrow a bunch of rev parts to make this actually. So let me show you real quick. So I go into my things. Of course I have a folder for everything that's just my stuff. So this stuff is pretty much hidden from everybody. So if you go to physics IA test rig, this will load in just a sec, but this is the test rig that has every single one of my components on it. So what you'll see is I actually have the joints hidden, so it's not so cumbersome to look at. But I can manipulate how these joints are functioning in CAD. Okay? Now some of these joints are rigidly connected, so I can't move these two apart. Like I can change the motion of this. But if you look, I just have these plates just on the extrusion. This is called an extrusion, by the way. But I have these plates on the extrusion. So what I would do to actually build the model is put screws in through these channels and put them through into the plate, then tighten the screws. Now you have a rigid connection. So I kind of like to classify like different building systems as fixed hole systems and variable slide systems. So Rev is variable slide because you don't have a really fixed position where things go, correct? You don't necessarily know, well, this plate will go all the way on this end, but you don't know how far that's going to be. You don't have fixed holes to, dictate your motion. So back to this Rev demonstration. The plate could be at any position on this channel depending on where you tighten and loosen it, which has a very good advantage of being extremely versatile. Like you can do some absolutely crazy stuff with this. For example, back in my 10th grade year, I actually built a robot that takes full advantage of how a rev works. Now, it's kind of lost a lot of cool functionality because simply because of time, like some of my parts got deleted for space, and it started messing with how my robot. You'll see in just a sec as it loads. So this was that robot, and if it wants to like do its thing, give it a sec. Um, so 5 components are out of date. I'm not gonna update that, trust me. But I kind of tried to use Rev's full capabilities to build this robot. Now the way that this works is, um, I took I took different Rev parts to secure them together, um, just like this, to make sure they are at angles. Now, and you really just need to use geometry here, right? You have one plate here, you have another plate here, and these plates need to be parallel. So if you want to make one higher than the other, like in real life, then you need to use the same angled bracket to make it parallel. Now, essentially, this was a muzzle loading robot that pulled a ring up and over and then shot it out from the same side. But I tried to use Rev's fullest capabilities here. Okay, but this is really what's possible with Rev. You can make an insane number of versatile objects. Now with Gobuilda creates some of the more crazy stuff. Yeah, that is the Peshbot's robot from Ultimate Goal. Um, don't tell anyone I said this, but I kind of carried in 10th grade. Um, because nobody else was gonna CAD the robot, and I was tired of being like made fun of. So I was like, okay, it's my turn to carry, and that's what happened. That robot is my pride and joy. Like that robot was fantastic. Even though it kind of sucked, it was like it was really game breaking because we didn't see any other robots that had muzzle loaded features. Everybody else was just shooting, like they were picking up robots from the or rings from the back and shooting them outwards. So they would pull in like that, which was kind of bad uh, because like like how are you supposed to function if the rings are rolling out the same direction that the goal is? It's like, well, then you're gonna have to spin you're gonna have to spin your robot around, pick up a thing, then spin it back, and then shoot. It's like what's the point of that? So we wanted to just make a different solution, and that's what we did. So anyway, now I'm gonna go into how Gobuilda works. So Gobuilda is a number of fixed holes. What that means is they literally take a aluminum channel and just bunch of drilled holes, right? It looks like this. I'm sorry if I sound like crazy right now. It's because I'm getting excited because like I'm the CAD guy. That's what people know me for. Anyway, you now have okay. So you can take a look at this channel. You can only have these set distances apart, which is something like I think it was like 8 millimeters apart, 4 or 8. Let's check actually. Wait, not like that. Circle, nah, bro. Circle. 8 millimeters. So each one of these holes is set off by 8 millimeters, and that's the step distance, right? That's basically how far things can go. So with Gobuilda, like, sure, it's versatile, but I don't really like it that much. Let me be honest. Even though it's like the new industry standard, it kind of secures you into a set path for how you can do things pre-built. So this is what I call pre-building. When you don't have 3D printed parts all over the place, then it's pre-built, right? But when you do have 3D printed parts all over the place, like right here, then those are custom parts. So I could never achieve a bunch of slide inserts with Misumi slides by using Go Builder parts. That just doesn't happen, right? So Go Build It kind of sets you into this path of how you want to how you have to do things.